All right, back to the momentum equation so I can explain what the Taylor-Proudman theorem is, and then explain what the thermal wind relation is, which is a case where the Taylor-Proudman theorem doesn't apply, but it's nice to contrast the two. All right, so let's go back to the momentum equations, which you will recall are given by this, dv dt. This is in the rotating coordinate frame, the frame fixed with the Earth, dv dt. The acceleration, this is the substantial derivative, the material derivative, plus 2 omega, where omega is the spin vector for the Earth, cross v is equal to minus 1 over rho grad p, which is the pressure force, minus grad phi, where phi here is the potential for the Earth, for the gravity and the centrifugal force, we can write as a potential. And the gradient of it, minus the gradient, gives us the force of the gravitational acceleration. And then the last one, plus nu del squared of v, the viscosity. All right, so that's our momentum equation. And the limit we're going to think about is a limit where the fluid is spinning very quickly, so omega is very big, and it's very big, and the velocity is relatively small, so that this acceleration term is small compared to the Coriolis force. So we're going to assume that this term is small. We're going to think about cases in which this term is small compared to this one, and also the viscous stresses are small also. So these two terms are small. So we're going to assumed small and neglected. Same thing over here. Assumed small and neglected. So we're thinking of, in terms of physical sharp, we think of scales of tens to hundreds and more kilometers, so large scales, and places where we can neglect the turbulent stresses to first order. So there'll be a balance between Coriolis, pressure force, and the gravitational force. And what we will do is take the curl of this equation. So this is a vector equation. So each term in this equation is a vector, and we can take the curl of that vector and see what we get. So if I do this, I will have del cross, after neglecting those terms, 2 omega cross v is equal to minus, and here when I take the curl of this, I'll use the quotient rule, rho times del cross grad p minus grad rho cross grad p all over rho squared minus del cross grad phi. And we can make some simplifications right away if we know, or if we try it out, that the curl of a gradient of a potential or of a scalar function is always vanishes. So del cross grad of anything, any function, this vanishes, and you can try it out and convince yourself that this is true. So this is 0. And we have a similar expression here where we have the curl of the gradient of P, of the pressure, and this also vanishes. What we are left with is this curl of the cross product of two vectors on this side, and the cross product of the gradient in rho and the gradient in P, or an expression involving the gradient of P crossed with the gradient of rho. So let's figure out what this expression is, and here there's a vector identity which we can use, which I will write out right now. So the curl of a cross product of two vectors, right, that can be written as the divergence of the second vector plus b dotted with the gradient of b. Of a. Minus, and there's a symmetry to it, minus, and then it's just to flip the symbols. The divergence of a plus a dotted with grad applied to B. So the first term here, the divergence of B, that's going to be a scalar. So it's a scalar times a vector, so we just rescale A by the divergence of B. The second term, this B dotted with grad, that's going to be a differential operator, and it's the derivative in the direction of B. So what we do, when we apply this to A, we take the derivative in the direction of B to all the components of A. So we see how A is changing in the direction of B. It's the directional derivative of A in the direction of B. And similar, we subtract, but now it's the divergence of A multiplied by B plus the directional derivative of B in the direction of A. All right, so we're going to apply this vector identity to this product, the curl of this cross product. And what we are left with is open parenthesis divergence of B, or B, which is just V in this case, plus V dotted with the gradient of 2 omega minus, and now we have the divergence of 2 omega plus 2 omega dotted with the gradient of V. That is this side. And then on the other side, what we have is grad rho cross grad P all over rho squared. And the rest vanishes. And now there's more terms that vanish. The omega vector is a constant vector, right? That's the spin of the Earth. It doesn't vary in space. The spin is what it is. And so the divergence of 2 omega just vanishes. So this is 0. Similarly, over here, the divergence of V, if the fluid is incompressible, then this vanishes. So this is 0 if the fluid is incompressible. Now, water is a little bit compressible, but to first order, water is a liquid, and liquids are not very compressible. So to a good approximation, the divergence of V is negligible for compared to the other terms in the expression. So this will give a very small term, and it's negligible. Then over here, we have the directional derivative again of 2 omega. So that also vanishes the same way divergence does, because this is a constant vector. So this term also vanishes, because omega is constant. And all we're left with in the end is 2 omega dotted with the gradient of V is equal to, minus, right? I have a minus over here. Grad rho cross grad P divided by rho squared. And I'm going to copy this above here somewhere because that's the main result. So let me write that neatly up here somewhere. So the result is 2 omega dotted with the gradient of the velocity is equal to, so there's a minus sign, right? If I bring the minus sign over to this side, and then I also, or if I interchange the order of grad rho and grad P, that will flip the sign. So A cross B is minus B cross A. So if I interchange the order of these two, I get a minus, and these minuses will cancel. So now I get the gradient of P crossed with grad rho. Notice that this used to be grad rho cross grad P. Now it's grad P cross grad rho. That introduced a minus, which I canceled with this minus all over rho squared. And this is the result I want. This formula here is the result from which we're going to get the Taylor-Proudman theorem. So the Taylor-Proudman theorem says that if the density is a function of pressure only, then in that case, the surfaces of constant pressure are going to be parallel to surfaces of constant density, right? Because if I give you the pressure, I can compute the density, and the density is constant along a surface of constant pressure. That means that the gradient of rho and the gradient of P are going to be parallel to each other. So they might have different lengths, but they're going to be pointing in the same direction. And in that case, grad P cross grad rho, that will vanish. And so if rho is a function of P, P and grad rho are parallel, and grad P cross grad rho is equal to 0. So this vanishes. And what we're left with is the result, which is the Taylor-Proudman theorem. 2 omega dotted with grad V is equal to 0. The 2 is not important. I can leave it out. Right? So scalar multiply. I can divide both sides by 2. And what the theorem says is that the shear, or the gradient of V, how the V changes in different directions, well, not in different directions. If I take the shear, or the gradient of V, in the direction of omega, of the spin axis, that vanishes. So in other words, there is no shear in the direction of the spin of the fluid, of the rotating chordate frame. And so this means that the fluid columns, the fluid, will act like rigid columns in the direction of the spin. So if we take omega to be if we imagine picking the Earth here, and this is the spin vector omega, and then this is the equator, and I pick direction phi, this is latitude, and I have a unit z hat vector in this direction, and I take the component of the spin perpendicular to the surface of the Earth, and I imagine that the other components, the horizontal ones, are negligible to first order in the fluid, like we explained last time. Then this here will be the vertical direction, and it says that to the extent that there is no, that this term vanishes, grad P and grad rho vanishes, that the surface of constant density and pressure are parallel to each other, then the fluid will move as a rigid column. So that's, to a first approximation, is a little bit the way the ocean works. So to first order, the density of water is a constant. I mean, it changes with pressure only. And so this term vanishes. This is called the baroclinic torque, by the way. And then there would be no shear, and the fluid would move like these rigid columns. So it moves, it can move horizontally. There can be horizontal shear. dV dx and dV dy don't have to be 0, but dV dz will vanish. And so you have fluid that's moving in rigid columns. And this is can be dramatically illustrated in a rotating tank. So you take a tank and you spin it very fast, and then you add drops of dye in it, and what you will see is that there will be some turbulence. The dye will move around, but like curtains. So in the vertical, there will be no, the fluid columns are moving like rigid curtains, and you see these beautiful swirls. And if you contrast that where the tank is at rest and you put the drops of dye, then the turbulence, I say at rest, not completely at rest, but not spinning, then you will form these clouds, and there'll be these three-dimensional structure. So in the spinning case, you get like two-dimensional turbulence with these swirls and curtains that are rigid in the vertical. Right, curtains, no shear in the component of the spin of the fluid. We have a 2D turbulence in the spinning case and kind of 3D turbulence in the non-spinning case. All right, so that's the result of the so-called Taylor-Proudman theorem. So this is the Taylor-Proudman theorem. You can see this in the ocean. Component of the vorticity of the, if we take omega to be the component of the spin perpendicular to the surface of the Earth, right? So if this is the Earth, this is omega, this is the equator, this is the latitude phi, and this is z hat. And then the component of omega in the direction of z hat, so is, or that vorticity can just be f times z hat. That's the spin, the local spin perpendicular to the surface of the Earth, where f, remember, is equal to 2 omega sine of latitude phi. And we're going to use that expression on this side and retain here the baroclinic torque terms. So what we have is f times z hat dotted with grad v. Right, so the z hat component of grad z will just be dV dz, just the vertical shear, is equal to, and on this side, to get the thermal wind, we're going to replace we're going to use the hydrostatic balance to place grad P. So hydrostatic is 0 is equal to minus 1 over rho grad, or dp dz, minus g, right? And so that means that grad P, or maybe I can write the whole thing. Oh, it means that grad P is just equal to rho g z hat minus rho g z hat, right? Pressure increases as we go down, so this expression tells me the grad P is minus rho g z hat. If I substitute grad P for that in here, what I'm left with is minus rho over, sorry, minus g over rho. One of the rho's will cancel. Z hat cross with grad rho. And this expression is the thermal wind relationship. This one is the thermal wind relationship. Thermal wind. And so it was developed in meteorology, so it's the wind, but it could be the thermal current. And in fact, in the ocean, density variations don't have to be just due to temperature, they can also be to salinity. So the name is more intuitive in the atmosphere, but it's the same physical principle relation. And what it says is that the shear in the vertical, right, will tend to tip the spin of the Earth. So the Earth, the spinning of the Earth gives it a vorticity, which we call the planetary vorticity, that spin, right? If you put a little paddle, the paddle would tend to spin because of from an inertial point of view, because of the spin of the Earth. So that planetary vorticity, the spin, the Earth is spinning this way. If there's a dvdz, right, it's going to cause that spin to tip over. So that tipping term is going to take spin, which is in this direction, and tip it into this plane, like this. And so what this would cause, this tipping would cause an overturning of the fluid. Would try to lift the fluid on one side and push down on the other one. This will happen if there's a baroclinicity in the fluid, or if the surfaces of grad rho, or sorry, if the gradient of rho doesn't vanish. So if there's horizontal, and it's the z hat cross grad rho, right? So this is going to be horizontal. What's going to be left over are going to be horizontal gradients of rho, right? Because we take the grad of rho and then we cross with z hat, and we're going to be left with horizontal gradients of rho. So if the density is not constant horizontally, then that means that the density surfaces will be tilted relative to geopotentials, and gravity is going to try to flip them back. So there'll be this baroclinic torque. So the surfaces are tilted, right? And gravity wants to make them parallel to geopotential surfaces. If you have dense fluid here and light fluid over here, the pressure forces will try to flatten it out to make the pressure surfaces and the density surfaces parallel, or density surface should be parallel to geopotential surfaces. This torque would want to make it overturn. But here we say there's a balance. In other words, that torque is going to be balanced by the tipping of the planetary vorticity. So the tipping is going to want to keep lifting up the density surfaces, dense fluid up on one side and more buoyant or lighter fluid on the other, downwards. And that trying to overturn is going to get balanced then by the gravity trying to pull these back to flat. So this balance is the thermal wind relationship, and it's what we see by this expression. So we can write it out in component form, right? The two components. So this side here, if I just take the z hat component of grad v, that's going to be f times du dz, and f times dv dz. So these are the two, and I guess the times dw dz. F times dw dz. That's the left-hand side. And on this side, what we get is minus g over rho times, and grad rho cross z hat. We can evaluate those components. So what I get, if I want to take this cross product, I have x hat, y hat, and z hat, crossed with so it's z, so the z vector is 0, 0, 1, just as a z hat component. Then the grad rho is d rho dx, d rho dy, d rho dz. Right? And I evaluate this. That will be, the first component will be minus d rho dy. So I get minus d rho dy. And then the next component will be minus y hat times minus d rho dx. So that will become plus d rho dx. And with the original plus plus, so this will become f du dz is equal to g over rho times d rho dy. And f dv dz is equal to minus g over rho d rho dx. So if we look at the first one, it says that if there's a north-south, if y is the northern direction, if there's a north-south density difference, then we would expect there would be a vertical shear in the eastward component of the velocity. Right? So if this is eastward, and I have fluid that's moving fast here and slow down here, then the spin of the Earth will get tipped over, and that tipping is going to cause the fluid to try to overturn in this direction. That means that as I go northward, right, this is eastward, as I go northward, the density should be increasing because I've lifted in the northward direction the more dense fluid from below, and on this side, the vortex tipping has pushed down the more buoyant fluid. That means that as I go northward, d rho d, or the density would be increasing, or d rho dy is going to be positive. And that's all consistent, right? It tells me that du dz is a positive shear. It's u is faster here than here, multiplied by f is going to be equal to g over rho d rho dy. And we can do the same kind of idea in this one. If I take now, if I'm going northward, so this is northward is into the board, and the fluid above is fast, and down here, I don't know if you can see me, down here is slower, then that's dv dz will be positive. That will take the Earth's spin and tip it, so that now we will have an overturning in this direction, and that will lift the dense fluid on the western side, push it down on the eastern side. So now if I do a d rho dx in this direction, then I'm going to go from the overturning as brought dense, less dense, so d rho dx will be negative, right? Will be negative, d rho dx, and then the negative will make the whole thing plus, so the sign again agrees. But it's more than just the sign works, is that it quantitatively gives us, if we can measure d rho dx, and we know g, rho, and f, we can compute what dv dz is. And so that's fundamental to how we analyze hydrographic data in the ocean. What we do is we get on the ship, we steam along, we drop CTD over the side of the ship, measure the density measure the temperature and the salinity as a function of depth or pressure. We then use the equation of state to compute the density as a function of depth. And we do this at all these stations along a ship track. And then we can compare one station to the next and see how the density changes at the same pressure level with depth. And now if there's a change in density on the same pressure level, then on that pressure level, that's a geopotential height, the change in density is going to cause gravity to want to accelerate the fluid from a region of high geopotential to a region of low geopotential, right? It's going to want to accelerate, from high to low geopotential. It's going to want to push the fluid downhill. But that pushing downhill, or that force, is going to be balanced by the Coriolis force, this vortex tipping term. And so we can compute what the vertical shear are in the ocean from these relationships. So write out recently there, little cartoon of what happens for hydrographic measurements at sea. So this is the sea surface, use blue, and we have a ship. And we drop the CTD over the side of the ship. All these bottles here, the rosette. And we take measurements at different depths. And then we keep sailing along and we make more measurements. And we keep sailing and we go make more measurements. And what we measure is temperature and salinity. Then we take the equation of state and we get the density, which is a function of T, S, and P. We have the density. Now we can make a map of the density, right? If we measure this sampling at a high enough resolution, we can now plot density surfaces, right? So I can plot, I'll make an imaginary set of density surfaces here. So the density would be something like this. Suppose we are going north and there's warm water over here and there's cold water at depth down here, and the surfaces of constant density look something like this. Right, so what we measured on the ship was T and S. We used the equation of state, got density, then we made a map, a cross-section map of the density, and what we notice is that the density is looking something like this. So it's more dense. This is the gradient of density is going in this direction. This is grad rho, right? We're going from less dense to more dense. And so that gradient of density, right, that gravity you would think would want to flatten these out, right? There's going to be a torque, right? It's going to try to bring these ones downwards and these ones upward, right? There should be a torque. And balancing that torque, there has to be this vortex tipping, this planetary vorticity tipping. So if F is spinning this way and we tilt it, we have a shear. If we have a shear where the current is fast and into the board up here and slower down here, and suppose it vanishes down there, then we have a shear which is tipping the spin into the board, and this is going to cause the spin tipping this way is going to cause the tipping torque, which is the opposite of this one, right? So the tipping over of F is going to do the opposite torque, this way and that way. And what we have is a balance of the tipping torque on this side, which is trying to overturn the fluid, lifting up the dense fluid on this side and pushing down on the buoyant water on this side. That tendency is going to be balanced by the opposite tendency, where gravity is going to say, wait a minute, it's going to try to pull down the more dense fluid downwards and flatten out these density surfaces. So that balance is the thermal wind balance, and it's the balance between a vorticity tipping, the planetary vorticity, tipped over into this plane, balances the baroclinic torque, which is gravity trying to make the density of constant, the surface of constant density be parallel to surfaces of constant pressure. All right.